Hello everyone, welcome to this week's session in which we will be turning our attention to regression. So I'm going to start off by just reminding you what we've considered so far, our analysis options when our independent variables are categorical. On the one hand, if our independent variables have been varied between participants, so that participants contribute only one data point to the analysis, we considered factorial analysis of variance using the general linear modelling approach. Last time round, we also considered our analysis options when we have an independent variable or variables that we have varied with a repeated measures element, where participants contribute more than one data point to the analysis. And we considered mixed models as an analysis option there. This time round, we're going to turn our attention to analysis options when our independent variables are instead continuous rather than categorical. And we may end up with continuous predictor variables, independent variables, for all sorts of reasons. It's actually quite common to have research designs that rely on continuously measured rather than directly manipulated independent variables. And that can be for all sorts of reasons. It may not be feasible practically or logistically to directly manipulate an independent variable. Or on the other hand, it might also not be ethically feasible to directly manipulate a variable that we think has an impact on an outcome variable that we're interested in. So some examples of research and theory that might imply continuous independent variables, continuously measured independent variables. For example, the theory of planned behavior, one of the most influential theories in the field of behavior and behavior change. A model based on the theory of planned behavior might suggest that we look at attitudes, perceived norms, and perceived behavioral control in relation to a particular behavior as predictors of those of intentions to perform that behavior. Another one might be somebody who's interested in whether somebody is willing to sign up as an organ donor, might look at the impact or the predictive role of emotional disgust reactions to the idea of organ donation, the so-called ick factor. It's hard to manipulate, so perhaps we measure it in a self-report questionnaire. Other factors might include demographic variables, which again, we can't directly manipulate, but we might be interested in as things that explain variance in outcomes of interest. So for instance, a political science researcher or a political psychologist might be interested in whether something like age or participant sex predicts political conservatism. Now, these are all different examples of research that implies that it's not going to be possible to directly manipulate or categorize our independent variables. Instead, we're going to measure them and use them as continuous predictors. Okay. So measuring them, such as disgust reactions in the organ donation example, we can also operationalize them in terms of pre-existing categories, such as participant sex. Now, technically speaking, if we haven't directly manipulated an independent variable, it's not, strictly speaking, an independent variable anymore, because the definition of an independent variable, the reason it's called independent, is that it is something that is varied or varies independently of any other variable in the analysis. It's instead under the direct control of the researcher. Okay, so anything that isn't directly manipulated by the researcher, strictly speaking, isn't an independent variable. So in the sorts of analyses that we will be considering today, it's more common to see the term predictor variable used rather than independent variable. Predictor in the sense that they are hypothesized to predict, or rather strictly speaking, predict variance in the dependent variable. And the dependent variable also often gets referred to as an outcome variable or an outcome measure rather than a dependent variable. I may switch in between those terms as we go along. I'm treating them as interchangeable, but just so you know that terminology may switch a little bit when you start to consider these sorts of research designs relative to the more experimental designs that we considered in the past couple of weeks. So another thing before we get into the practicalities of these analyses is thinking about how we represent our hypotheses, the models that we're going to test. And in designs or analyses that involve several different measured predictors, we often summarize those hypotheses in terms of path models that summarize the predictive relations amongst the variables. So we might specify an outcome variable. We might be interested in trying to explain people's intentions to perform a particular behavior, maybe healthy eating or going to the gym, whatever it might be. And we identify a set of possible predictors of those behavioral intentions. And we specify that each of those are expected, hypothesized to have a unique predictive effect on the outcome variable. So, for various different reasons, the connection between what you're testing and good design and theorizing is really, really crucial. Okay? Because when we're talking about measured rather than directly manipulated independent variables or predictors, there might well be very good reason to hypothesize that one variable, variable A, affects variable B. But if we have only measured rather than directly manipulated variable A, we cannot be certain that the relationship is causal. Okay. That association, any association between variable A and variable B, might be because of some other unmeasured factor. They may both themselves be outcomes of some other process that we haven't assessed. Or the causal relationship might even be reversed. It might be B affecting A rather than A affecting B. Okay. So the crucial thing here to bear in mind is that in all of the analyses that I will be talking about in these sessions, a significant effect in regression cannot distinguish or establish causal relations. Okay. Only predictive relations in the sense that A predicts B. And in turn, just to clarify that, when we say that A predicts B, that is predict in a statistical sense. Okay. We can know or infer something about values of B if we know something about values of A. For example, if they're higher, we might expect higher scores on B or lower scores on B if A is lower. Okay. So for those reasons, the specification and the interpretation of a regression model rests really heavily on good theory-based reasoning and hypotheses. Okay. It is really important to think, as we will see, not just about the nature of relations between your predictor variables and an outcome variable, but also between your independent variables, those predictive variables. How do they actually relate to one another? Okay, that will be a recurring theme this week and in the next couple of weeks too. So let's reintroduce regression a little bit more specifically. Now some of this in the early stages will be somewhat familiar to you. It will be covering ground that you will have probably covered in previous years. But the idea is to give just a bit of a refresher that provides a basis for going into the new directions that we will later on in this session and in the next couple of weeks. So, in essence, a regression analysis tests whether one or more predictive variables predicts, not causes, but predicts variation in an outcome variable, a dependent variable. So some of the assumptions here, and as I said in the introductory week, I won't be going into any of these assumptions in any detail, but just I'm flagging them again here. Some of the assumptions in regression analyses are very similar to those of other parametric approaches like analysis of variance, others under that umbrella of the general linear modeling approach. So it assumes, for example, that scores on our variables, predictor and outcome, are normally distributed and that observations are independent. Some other specific assumptions to linear regression, we're assuming that the association between a predictor and an outcome is linear, although it is actually quite possible to conduct non-linear analyses in regression. It's just we won't be covering them in this module. Another assumption is that of homoscedasticity, which is very similar to the idea of equality of variances, or rather equality of variance in residuals in analysis of variance. And that's basically the idea that as we move to different parts of a regression curve or a regression fit line, people's variation from that will be equally variable at different points on that line. Another thing to just flag about regression before we get into it practically is regression gives you, or regression analyses give you, an awful lot of information. So what you want to extract from that information and what you want to emphasize perhaps in a write-up of that set of results will depend very much on the details, the precise details of the research question that you're asking. If, for example, we are interested in whether a predictor significantly predicts a dependent variable, in other words, is the slope, the slope of the best fitting line that summarizes the association between those two variables, is that significantly different from 0? For that, we might look at the t-test in the regression table and the associated p-value. We might also, or instead, be more interested in the strength and the direction of the predictive relationship. Not just is it significantly different from 0, but how big is it? Okay, and is it a positive association or a negative association? Okay, for that, we might look at the standardized and the unstandardized regression coefficients. We might also be interested in another sort of aspect of effect size, which is how much variance in the outcome variable is explained by the model. Okay, how much variance is explained in our outcome variable by, the predictor in our model, predictors in our model. Okay, for that we might look at the R-squared value, and in multiple regression we might look at the R-squared adjusted value, the adjusted R-squared value. And we might also be interested in what regression equation best summarizes the relationship. Okay, if you want maybe to work out predicted values for individuals, or based on knowledge of specific scores on a predictive variable, for instance, we might look at the regression equation, which is the intercept, okay, A, plus the regression coefficient, the unstandardized regression coefficient, multiplied by an individual score on the predictor variable. Okay, and that will give you the best estimate based on the regression model, the regression equation, of what their score on the outcome variable will be. When we turn to multiple regression, where we have more than one predictor in our model, we might ask additional questions, additional things we're able to infer from the output. We might be interested in whether a predictor significantly predicts an outcome variable. Is that slope significantly different from 0 when controlling for or adjusting for? I might use controlling for and adjusting for interchangeably. I mean the same thing by those. Adjusting for or controlling for other predictors in the model. So not just does A predict B, but does A predict B when we're controlling for other predictors like C, D, and E. Again, we will look for the t-test and the p-value in the regression table for that, for each individual predictor. We might be interested in whether the overall model is significant. In other words, is the amount of variance explained in the outcome variable by the model, that set of predictors as a whole, significantly different from 0? And for that, we might look at the ANOVA table. And finally, we might be interested, when we have more than one predictor, we might be interested in how much variance in the outcome variable is explained by each of those predictors, not just the model overall, but each of them. Okay, and for that, as we will see later on in relation to hierarchical regression, we might look at the change in R-squared score. Okay, in other words, the change in R-squared, the change in the amount of variance accounted for in the outcome variable, by adding or removing individual predictors. Okay, what's the effect of adding or removing individual predictors from the model? So, to get us into the practicalities, the actual doing of the analyses, once again, I'm going to start with a research question, look at it in the most simple terms design-wise, and then look at how our analysis options and implications change as we add some complexity and nuance at each step. Okay, so this time round I'm going to start with this research question, something that maybe an organizational psychologist or someone working in a business school might be interested in. Okay, what predicts commitment to an organization, employees' commitment to an organization, and specifically does their sense of identification with the organization, that sense that being part of that organization is part of who they are, does that predict commitment to an organization? So, in the most simple design, what they might do is predict that stronger identification with the organization will predict stronger commitment. The more you identify with the organization, the more committed you will be. Okay. So schematically, that's very simply represented as follows. We've got a predictor variable, identification, and an outcome variable, commitment. And we expect that predictive relationship, that association, to be positive. The researcher takes questionnaire, self-report measures of both of those variables, so they're both continuous, and their analysis options there, well, given the hypothesized relationship, they go for linear regression, a simple linear regression. So let's have a look at that in action. Okay, so here we've got a data set. Now to run a simple regression, or I guess any type of regression, we go to regression and find linear regression. Okay. So we've got commitment as our dependent variable, our outcome variable. And you've got two options here for entering predictors. Okay. And it's slightly unintuitive language, but in the covariates box, that's where you enter any predictor that is continuous, okay, indicated by this little icon here. Under factors, that's where you enter any predictor that is categorical. That's something we'll come on to later in this session. For now though, we only have one predictor, and that is organizational identification. That's continuous, so it's going in the covariates box. Now, some other useful things to select over and above the default. Under model fit, okay, choose adjusted R-squared as well, and also the overall model test, the F test. Under model coefficients, also ask for the estimate confidence interval and also the standardized estimate. The standardized estimate is the beta, the so-called beta coefficient, which I'll go on to in a moment. Okay, and there is our outcome. Okay, just to pick up a few key details there. From that ANOVA table, we've got our R-squared and our adjusted R-squared. Okay, these will be very similar in a simple linear regression, but when we have more than one predictor, it's the adjusted R-squared that is preferable. If you recall, an R-squared will always go up as we add predictor variables to a model, even if those predictors in turn themselves don't individually explain anything meaningful in terms of the outcome variable. Okay, the adjusted R-squared corrects for that. It corrects for the number of predictors in the model and starts to penalize you as you chuck extra predictors into the model. Okay, so the adjusted R-squared overall is generally preferable. Okay, and just to reiterate, this is a proportion, so we can also multiply it by 100 to express it as a percentage. Okay, so in this case we have 39% of the variance in commitment explained by identification. Okay, the overall model here, this is interpretable as an ANOVA effect. There's your F ratio, your numerator degree of freedom, and your denominator degrees of freedom, and the p-value. Okay, so that's the significance of the overall model. Does the amount of variance explained in the outcome differ significantly from zero? In this case, yes, definitely. Turning to the model coefficients table, we've got firstly the unstandardized regression coefficient. Okay, that's under estimate. So the value under the estimate column is the unstandardized regression coefficient. And right over on this side then we have the standardized estimate, the so-called beta coefficient. All right, so this is an unstandardized B coefficient, and this is the standardized beta coefficient, the Greek letter beta. Okay, so just to reiterate what each of those means, the standardized coefficient is the unit change you would see in the outcome variable for a 1 unit increase in the predictive variable. Okay, so in this case, as identification goes up by 1 unit, you'd expect a 0.62 unit increase in commitment. Okay, Now the standardized coefficient expresses the same relationship, but assuming that both measures had been standardized. In other words, they've been transformed so that they had a mean of 0 and a standard deviation of 1. Okay, so it expresses the association in terms of standard deviations. So a 1 standard deviation increase in identification is associated with a 0.63 standard deviation increase in commitment. Okay, and there we have the significance of the predictor based on the t-statistic. The other thing here is if you know the unstandardized estimate, the unstandardized regression coefficient, and the standard error, you can always work out the t-statistic. All right, it's simply this divided by this. That gives you the t-statistic. And if we wanted to formally write out a regression equation, okay, we can specify that the intercept is 1.68. That's this value here. The coefficient for the intercept, okay, and the unstandardized regression coefficient for identification multiplied by identification score. Okay, so if we know somebody's score on identification, we can, with this equation, have a stab at guessing what their score and commitment might be. So at this juncture, I just want to point out the similarities between correlation and regression, especially simple linear regression. So correlation and simple linear regression are very similar. In fact, they're functionally equivalent. They are functionally the same thing. Okay. Again, once more, they are just different instantiations of a general linear modeling approach to looking at the association or effects between two variables. Okay. So why would you choose one over the other? Well, often it's to do with the precision or the sort of the specificities of your research question. Do you have reason to suspect that the relationship might be causal, even though your design itself doesn't allow you to establish that? Or do you think that maybe there isn't actually a clear theoretical reason why the two variables are related in a cause and effect manner? Okay, if they're simply associated, okay, then we might look at correlation rather than regression. But let's look at the similarities. So I'm just going to pop back to the data set. Okay, and I'm going to run a correlation looking at the association between commitment and identification. Now, slightly confusingly, correlation options live under regression in jamovi. So we'll choose correlation matrix this time. Okay, and we're going to look at identification and its association with commitment. Okay, there we go. So just a couple of things to flag. Here's the output from the correlation, and here's the output we just looked at for the linear regression. First thing is that the R, okay, the R value, the correlation coefficient, is exactly the same as the standardized regression coefficient. Okay, in a linear regression, the standardized regression coefficient is the correlation coefficient. That's what it is. Okay, and it's also the same as the R value you get in the model fit table. Okay, so when we talk about R squared, the thing that we're squaring there is R, and that is simply the correlation coefficient. So it also follows from that, if we run a correlation, we can also work out the R squared value that we would get if we had run it as a regression. Okay, so the amount of variance from a correlation, you can estimate the amount of variance overlapping between the predictor, by one of the variables and the second variable. Okay, in this case, you simply square the R, square the correlation coefficient. 0.63 squared gives you 0.40. All right. So they are functionally the same thing, correlation and linear regression. So a regression approach comes into its own more when we have a more complex model, when we add more complexity or nuance on the predictive side of things. So let's go back to that research question and extend the design a bit. Let's say that the researcher wasn't just interested in whether a stronger organizational commitment would predict stronger organizational identification would predict stronger commitments, but that would happen over and above, or controlling for, adjusting for, other factors such as their job satisfaction, the amount of salary they get, or age and sex as potential demographic predictors of commitment. Okay, so again, I'm using another term for controlling for and adjusting for. So whenever we say over and above in the context of regression, what I simply mean is controlling for or adjusting for the over and above thing. Okay, so to say that we're testing whether identification predicts commitment over and above these other factors, what I mean is controlling for or adjusting for them. Again, a researcher might take questionnaire self-report measures of all variables, as well as their age and sex. Okay, salary here is operationalized in terms of annual salary before tax, and they might draw out their model schematically. So we've got their outcome variable, commitment, and each of these will be entered into the model as a predictor of commitment. Analysis options wise, multiple regression. So that allows the researcher to test the role or examine the role of each individual predictor, particularly identification, while also adjusting for the role of other predictors and assessing the overall fit of the model. Okay, does the model as a whole, this set of predictors together, explain a non-zero amount of variance in commitment? Okay, so let's go back to our data set and run that model. Okay, so again, we're going to regression, a linear regression again. We have commitment once more as our dependent variable. We've got identification as our first covariate, but we're also going to enter annual salary and job satisfaction and age as covariates as well. Okay. Now, we have participant sex here. Now, because participants only reported being male or female, sex is treated as binary. Okay, in this case. And you actually have, for a binary categorical predictor, you've got a couple of options. I would generally recommend entering it as a factor. Okay, so let's just have a look at that. The p-value for sex is 0.438. But if it's binary, a categorical predictor can also be entered as a covariate. And you will get the same outcome, okay? The same effect. 0.438, its effect. But by default, best to put it in the factors box. So let's just ask for those extra things that I pointed out before. The adjusted R-squared, the F-test, the confidence intervals for our unstandardized estimate, and then finally for the standardized estimate, okay, the beta coefficients. Okay, so let's pick out a few key details here. Here's that model fit table where the adjusted R-squared suggests that the model explains 46.5 or 47% of the variance in commitment. The overall model is significant, so that model as a whole with that set of predictors explains an amount of variance in the outcome that is significantly different from zero. Okay, that's the F ratio, degrees of freedom, and the p-value. Let's turn our attention now to the model coefficients table. Organizational identification is still a significant positive predictor. Okay, so as identification goes up by 1 unit, commitment goes up by 0.38 units. Okay, still highly significant. Annual salary and job satisfaction are also independently significant positive predictors. Okay, T statistic and the p-value suggests that the slope of the relation between annual salary and commitment and job satisfaction and commitment is significantly different from zero. Okay, and finally, our two demographic predictors, age and sex, do not significantly predict commitment. Okay, non-significant for age and non-significant for sex. Now, just to reiterate, excuse me, the specific meaning of the coefficients and significance in multiple regression, where you're adjusting for other predictors. The coefficients indicate whether an independent variable, and the significance of that, indicates whether an independent variable predicts or explains a unique part of the variance in the outcome variable. In other words, does it explain part of the variance in the outcome variable that is distinct from the parts explained by other independent variables or predictors in the model? And that's estimated in turn when those other predictors are held constant. That's what controlling for means, adjusting for means, when they're held constant at their mean value if they're continuous, or at the reference category value if they are categorical. Okay, so that's specifically, in slightly more specific terms, what the coefficient and its significance means. Significance in a statistical sense means. Okay. Now, just to close off this first part, I'm going to throw what might be a little bit of a curveball. Okay, I'm going to run the same analysis, that same model again, but now using analysis of variance, using that general linear modeling approach that I showed when running between participants ANOVA. Okay, so I'm just going to pop back to the data set. Okay, and rather than choosing regression, I'm going to general linear model. Linear models, general linear model. Okay, I'm going to specify commitment as a dependent variable. Sex is a factor, because binary in this case. And we have our 4 continuous predictors, which I'm going to enter as covariates. Okay. And there's the ANOVA table and the parameter estimates table. So let's just pop back and look at those. What do we get? We get exactly the same outcomes. The R-squared and adjusted R-squared values are identical to the regression analysis. The p-values for each individual predictor are identical, and the F ratio you get in the ANOVA table is simply the t-statistic from the regression table squared. Okay. And in fact, if we then look at the parameter estimates table from the ANOVA output, it's basically the regression table that we looked at. We have identical unstandardized and standardized regression coefficients. We have the same standard errors, confidence intervals, t-statistics, and p-values. Okay. So why? Okay. Well, again, key message of the module: analysis of variance, multiple regression, and indeed anything else that we're going to talk about for the remainder of this module are both just versions of the general linear modeling approach to analysis. ANOVA, as we've done it, is effectively a form of regression. All right. So the implication here is that pretty much any linear multiple regression analysis can in principle be done using ANOVA, and vice versa. All right. So they are not fundamentally different things. And actually, the reason that you would choose, or I would choose, one approach over the other is simply a pragmatic one, to do with how easy or difficult it is to extract relevant information from the output. And that depends, in turn, that's informed by my research question. All right. So again, key message: multiple regression, ANOVA, correlation, everything else in this module is just a form of general linear modeling. All right. So we'll leave it there for this part. Join me again in part 2, where we'll be starting to look at hierarchical multiple regression. Okay, join me then.